it gets to you. Okay, we're supposedly recording. And that's good, I guess. Okay, how many people do we have? Okay. All right, so we've talked about what sequences are. So just not very mathematically, but just writing down things. We have a sequence. More mathematically, a sequence is a function which has domain, usually the natural numbers. The natural numbers actually are like 1, 2, 3, and so on. So they're real valued, and so that's what we do. And instead of writing f of n, we usually write something like a sub n. Okay, so we have a function. There's a first thing, a second thing, a third thing. That's what we mean by saying there's a function. And if we wrote them out, if we write a list out, you get a bunch of things in succession. Okay, these things are called terms of the sequence. You know all that. Okay, well, so I'm going to assume that I'm given such a thing. I'm given a sequence of numbers. All right, some formula probably. And we're going to define something new. Namely, I'm going to define S1 to be A1. I'm going to define S2 to be S1 plus A2. I'm going to define S3 to be S2 plus A3, and so on. So what am I doing? Yes, thank you. So, yes, good. Wait, okay. Peter, as soon as you can hear me, I'm letting you in much earlier than yesterday. Peter was the other person who was probably out for the whole period trying to bang on the door to get in. Anyway, somebody just noticed that you hadn't gotten in yet, Peter, so now you're here. So please look at the video yesterday in case you missed most of yesterday. There's nothing I can do about it, but I feel bad. Oh, I'll give you 15 extra points on the next test.
Yay.
So now everybody's going to be outside and want to get in, right? Anyway, we have a new sequence. Now, this is a little bit disguised, but of course, S1 is A1, so this is A1 plus A2. S2 is A1 plus A2, so this is A1 plus A2 plus A3. Okay, and so what this is called a sequence, because that's what it is, of partial sums of the sequence A. So we're building a second sequence from the first sequence. And the second sequence is taking, as I said, what we call partial sums, because we're not adding up the whole sequence here. Okay, so let me write that over here. If I wanted to write something like that, I might write dot, dot, dots, but what we use, as you know, is a sigma. And so I might write for this thing, whatever it means, I might write this symbol. Yes, somebody else. Luke wants to get in. Luke was here yesterday, I think. Come on, machine. Shouldn't take 3 hits to do that. Anyway, so if I were to write down, adding up all of them some way, I can't, of course, write it all down. So sooner or later, I put dots. Right. This would be trying to say add them all up, whatever that would mean. Symbolically, we use, for sums, we use a sigma. So we would say add them up from 1 to infinity, because that just means keep doing it. Okay. So this means that, but neither of them has a meaning because we haven't talked about what we could possibly mean by adding up an infinite number of things. We don't know. But this would be the symbolism for that if we tried to define it, okay? Well, we are trying to define it. That's over here. Okay? So these are the things we are heading toward over here. This is the stuff we're going to use to get there. So this series, this thing would be the whole, add them all up. This is called an infinite series. Why the word infinite? Because we keep adding. So people named that early on before they even knew what infinite was. This just means keep going over there. If I talk about these things, adding up three things would be called a finite series. So the word series in English means add up. Sum, find the sum of. And it's easy to find the sum of a finite number of things. We haven't yet discovered how to find a sum of an infinite number of things. That's what we're trying to do. Okay, so we have a new sequence called the sequence of partial sums. And so it would be delineated by something like this. It's a new sequence. Now, this sequence of partial sums is called, okay, the series of the A sub k. And if you like, it's called the infinite series. So the answer to what in the world does this mean? An infinite series is a sequence of partial sums. It is best not to think about adding up an infinite number of things. It is best to think about adding up partial sums and seeing what that sequence looks like. Okay? Now, there are a couple of problems that come up because this new series, the S's are now the terms of the new series. And so a series has two sets of terms. In other words, as a sequence, the series has terms S sub n, S sub 1, S sub 2, S sub 3, S sub 4. But as a sort of trying to add up a bunch of things, those things are terms also, and those are terms of the original. So a series is involved with two sequences and two sets of terms. And so sometimes when somebody says, what's the first term of the series? Well, that's pretty easy because the first term of the series is the first term A1, and it's the first term S1, it's the same thing. But if I ask you, what's the second term of the series, do I mean A2 or do I mean S2? And because we might mean either thing because we're sloppy, you got to be careful when somebody says, what's the term? Because the A's can be terms and the S's can be terms depending on which one we are thinking about. Okay? So you have to be careful about that. And some books are very specific about it and some books are ambiguous. So you have to always look at your definitions to see what they are saying, and then you stick with it for that particular setup. Anyway, we have a sequence of partial sums. So, for example, if my original sequence is 1 over, I've been using k for the original. If it's 1 over k from 1 to infinity, what's that sequence? That's 1, 1/2, 1/3, 1/4, and so on. That particular sequence has a limit of 0. That just happens. That's what it is. I'm not saying it's relevant to our question, but we could find the limit of that sequence. Okay? If I make up a series from those terms, now I have a thing which I write this way. Okay, now we have our second problem. So let me explain it a little bit differently. and I said something to somebody yesterday, but suppose that I write this on the board up here. Yeah. And I ask you, what is this? I presume some of you would say 7, because that's what it is. You'd argue with me. And I think some of you say it's 3 plus 4. Because what I wrote is 3 plus 4. And if I ask you, what is this? Do I mean to do something to find out what it means by combining things, or all I'm asking is, what did I actually write? And so you could get confused here between the question and the answer. So do I want you to say 3 plus 4? Do I want you to say 7? I don't know, okay? That's the ambiguity here. Okay, so when I write this thing down here, this tells you what the AKs are. This symbolism tells you what these are, right? It doesn't tell you what the S's are. But you can, when you see this, you can find out what the S's are. S1 is 1, S2 is 1 plus a half, S3 is 1 plus a half plus a third. So this notation for a series tells me what the original terms A are. Okay? But it doesn't tell me what the partial sums are. I have to construct those. But the problem is we use this for the name of the series, for identifying what series we're talking about. The problem lies in the fact that we also use the same symbol if there is a number that the partial sequence of partial sums over here. A minute ago, I said, hey, I can write a limit of the terms over here. Now, over here, I have a new sequence. I can write the limit of these terms. Okay? Because I got another sequence. And what we do with sequences so far in section 1 is take limits. So I can take the limit of the sequence of partial sums if I want to. I don't know it exists, but I can try it. Or I can take the limit of the original terms that make up the partial sums. So I got 2 different limits I can consider. Okay? And what we say is that the infinite series converges if the limit of the sequence of partial sums exists. Okay? In other words, if this limit exists, we say that's just the limit of a sequence. But if it exists, we say the series converges. And the limit of the sequence of partial sums is called the sum of the series. So the limit of the sequence of partial sums is called the sum of the series if it exists. If the limit exists. Now, if the limit exists and the series converges, the name for the answer, the sum, is the same symbolism. In other words, this symbolism can mean the thing before you add it up, that was the 3 plus 4, right? This can mean 3 plus 4. This same symbolism can also mean 7. Because 3 plus 4 also means 7, if you think about it. Okay? So we use the same thing, unfortunately, to mean both the question and the answer, if there is one. In this particular problem, we're going to find out that this does not exist. Now, when I say that, I mean the series does not have a sum. This series diverges. Let's see if we can figure that out. Since I'm talking about it, let's talk about that a second. Let's see if we can figure out what the sequence of partial sums look like of that particular thing. Now, I'm going to write some down here, but I'm going to stop because you get tired. I'm hoping you see this would be the sequence of partial sums. Now, I'm going to call this S1, this is S2, this is S3. Okay. Let's talk about S2, S4, S8, and S16. Now, that's not all of them, that's just some of them. But S2, that's 1 plus a half. I can actually add that up, that's 3 halves. Okay, so now, by the way, this series, the original terms are positive. You know that, 1, a half, a third are all positive. And it's going to turn out that we're going to distinguish later series that have all positive terms and series that have different collections of positive and negative. Okay, right now they're all positive. This 1 over k is 1, 1 half, 1 third, we'll go all positive. So if you look at it, it's easy to see this is an increasing sequence. The sequence S's is increasing because each time we're adding a bigger positive, not bigger, a smaller positive number, we're adding a positive number. This is increasing, so the sequence of partial sums is increasing. Okay, it will have a limit only if it's bounded above, because when an increasing sequence is bounded above, it has a limit. Now, what is S4? S4 is 1 plus a half plus a third plus a fourth. And that is 3 halves. Now, I don't want to add a third and a fourth, that's much trouble. I'm going to say this is greater than a fourth plus a fourth. Because if I replace a third by 1/4, I'm replacing a bigger number by a smaller number. Okay, so S4 is bigger than 3 halves plus a fourth, and that is 2. So S4 is bigger than 2. Okay, what's S8? S8 is S4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. Right? And that is greater than 2 plus 1/2, because 1/5 is bigger than 1/8, 1/6 is bigger than 1/8, 1/7 is bigger than 1/8. So I have a number here, 1/6 plus 1/7 and so on, is bigger than 4/8. That's a half. So this is bigger than 2 1/2. S16, you can show, is bigger than 3. So what? What do you think S32 is going to be? Bigger than 3 1/2. What's S64 going to be? Bigger than 4. Okay? That kind of thinking will lead you to believe if I keep going forever, I'm going to keep getting bigger and bigger and bigger. This is not going to converge. And it won't. You tell me how big you want it to be, I'll tell you how many terms I have to keep. Because I can work out a formula here for how big this is compared to what this number is. Okay? If 16 is bigger than 3, that's 2 to the 4th. Okay, if 8 is 2 to the 3rd, that's bigger than 2 1/2. I can work out a relationship here You tell me, I want to know if I want to get bigger than 1,000, I'll tell you how many things you have to add up to get bigger than that. I can compute it. I don't want to compute it, but I can. So this series diverges. And the problem is that humans are not very good at predicting if you have a sequence of partial sums, do they add up to something? If you can keep going forever. Okay. Now, if we stuck to a principle that each day I'm trying to drive home, and each day I go half the distance remaining, will I ever get there? Well, I won't get there in a finite set of days. If the days could go, if I could have an infinite number of days, and at my age, I wish I did. If I had an infinite number of days, I might just get up to the place. Do you understand? Let's see if we can figure that out. Not about days, but just suppose that I try to figure out the series 1 plus a half plus a fourth plus an eighth plus a 16th. Suppose. Right? So I have the series. How can I write that down? I can write that down as powers of 2, 1 over 2 to the k, maybe? What do you think? Now, if I leave it this way, I don't get all of these. When k is 1 here, I have a half. When k is 2, I have a fourth. When k is 3, I have an eighth. So this, so far, what I've written, I have all of these, but I don't have 1. If I want 1, I can just add 1 to it. That was it. I got it, did it. If I want to make it part of the series, I'd have to change this in one way to 0 to infinity. 1 over 2 to the 0, that's 1. So this would work. So this would be writing the series at starting at 0 instead of starting at 1. And sometimes we might want to do that. On the other hand, if you want to always start at 1, I could change this to k equals 1 to infinity, 1 over 2 to the k minus 1. This one, if I let k be 1, I get 1 over 2 to the 0, which is 1. If I let k be 2, I get 1 over 2, that's a half. This actually is that. This one isn't, this one is. This one's missing 1 term, original term, right? Okay, but if I can write, and yesterday we did something about that. If I can write, so I have a series, k from 1 to infinity, 1 over 2 to the k minus 1. All right? Now, I'm gonna, that's the name of it. That doesn't mean it has an answer, right? That's the problem. I want to find out, does this converge? If it converges, I'll say that's the answer as well. That's the name of the answer. Okay. So, suppose I believe there is an answer. And let's call it L. I believe there's an answer. If I would multiply that answer by a half, what would happen? So I'm going to write this. This is 1 plus a half plus a fourth plus an eighth, 16th, and so on. If I had multiplied this answer by a half, at least for the partial sums, the partial sums arithmetic works. We don't know if it works for the whole thing or not. This is why we don't really want to do this. We want to take limits. I don't want to keep doing this adding thing because I'm not very good at it. I'm trying to illustrate why I'm not very good at it. But if I took half of things, I would get half of things would be a half plus a fourth plus an 8 plus a 16th, right? And if I subtracted all of them, I would get a half L is, I subtract these from those, this would disappear, and this would disappear, and this would disappear. I'd be just left with 1, so L is 2. So if I assume there is an answer, I can find out that the only possible answer would be 2. Okay? Now, that's cheating because I don't know about taking half of an infinite number of things. So what I'm doing is not correct, but it makes me believe that 1 plus a half plus a fourth plus an 8 might add up to 2 if I could keep doing it forever. Now, why does this bother me? We're going to make it correct in a minute. But why does this bother me? Because I don't see much difference personally. Maybe you do because you're smarter than me. I don't see much difference when I look at these things as to why this would be infinite and this would be 2. It just doesn't seem to me that these numbers ought to add up to 2 and these ought to add up to infinity. It's not, they're not that different. So what I'm trying to get at here is humans don't have any intuition about this. At least this human doesn't. You guys might be able to say, oh, no, I can see the difference. Okay, I can see the difference, but I can't see a difference that would be between 2 and infinity, personally. Okay? And if you're not as smart as me, well, then you're dead, see, no problem. If you're smarter than me, maybe you can see it. I don't know, I can't. So I got to survive in this world because I'm supposed to know what I'm doing. So I got to have some way to work this out that I can trust. And so the thing to do here is not to do this for an infinite number. The thing to do is to do it for a finite number because there the arithmetic works. And so S sub n is the sum from 1 to n of 1 over 2 to the k minus 1. Now that's only the first thing. That's the nth partial sum. So S1 would just be 1. S2 would be 1 plus a half. S3 would be 1 plus a half plus a fourth. And I can do with this the same thing I did before. I take a half of it, but now I can multiply a half into the sum because I only have a finite number of them. And when I do that, when I multiply by half over here, I will get the sum from 1 to n of just 1 over 2 to the k. Okay? And now, if I subtract the second one from the first, I don't have much practice in this, but I want you to develop the ability to do this. I need to figure out how to write these things, because I'm taking the second thing from the first thing. They both go from 1 to n, but this is 2 to the k minus 1, and this is 2 to the k. Now, if I would change the meaning of this, if I up the meaning of the index and rewrite this as k from 2 to n plus 1 and decrease the meaning of the index over there, I get the same thing. If you look, when k is 1, I get 2 to the 1. When k is 2, I get 2 to the 1. When k is 2, I get 2 squared. Here, k is 3, I get 2 squared. I get the same thing. At the end, I have 1 over 2 to the n. When k is n plus 1, I have 1 over 2 to the n. I get the same thing. These two things are equal. But they give me something I didn't have before. Namely, if you look at the two things written over here, this is the sum from 1 to n of 1 over 2k minus 1 minus the sum from 2 to n plus 1 of 1 over 2 to the k minus 1. And the point I want to make out here is the same thing. But these are different. So I'm going to split one of these off. I'm going to make this 1 over 2 to the 0 plus the sum from 2 to n. And just split these up. The first one I took off and I have 2. The reason to do that is because over here I have 2. But over here I'm going to take off the sum from 2, and I'm going to say to n, 1 over 2 to the k minus 1, minus 1 over 2 to the n. Because if I split the last one off of this finite sum, the last one is when k is n plus 1, and that k minus 1 would be n. So this right here is the same as that, and this is the same as that. So I got the same thing. So I'm going to simplify now. I get 1 over 1. And what do I get here? Well, this thing and this thing are identical. They subtract and give me 0. So I get 1 over minus 2 to the n. Okay. Now I got I have a problem here somewhere that I don't see at the moment, because I ought to get 2 here instead of 1. Anyway, because a minute ago we said the limit was 2. So what did I do here wrong? I did something wrong, but what the game here is as follows. I replace these sums by a number which I can take a limit of. Okay? And this limit of this is 1 in this case. It should be 2. And yeah, there's a mistake up here. But the point is, the idea of series is not to sum up an infinite number of things. It's to sum up the partial sums and take a limit. The limit of the partial sums humans have a good idea about. If I have this term, I can write this as n gets bigger and bigger and bigger. I can see where this goes. Now, somebody's going to tell me about the mistake I made. Where did I make the mistake?
Everything you did is correct, but you're solving for 1/2 of Sn, so 1 would be the correct answer.
So.
Because what you're solving for right now is S minus 1/2 of Sn on the line below where you are now.
Right. So it's 1/2 of this. What did I make the?
Well, the limit of 1/2 of Sn should be 1, because the limit of S of n is 2.
Okay, so this is not a mistake.
No, it's all, everything you did is right.
Okay, that's good. Anyway, when you step back from it, you can see what I'm talking about. So the limit of Sn, as is said, as n goes to infinity, is 1, and that you can see. Okay, so why does that make the series converge to 2?
Dr. Brady, see on the bottom line at the left side of the blackboard? Yes, and then the line just above that. What you're solving for here on the right side of the blackboard is S minus 1/2 of Sn, which equals 1/2 of Sn.
Yes, thank you. Now this is 1/2 of Sn. Yeah, okay, so the limit is 1, but it's half of Sn. So the limit of Sn would be 2. That's what we're saying. Yeah, okay, thank you. Yeah, I just didn't write this over here, and yeah. Okay. Why don't the rest of you see it? Anyway, the point here is that instead of adding up an infinite number of things, I took the limit of a sequence. Now, I have to be careful about that because I had to see what I get over here. But the key here is not to put infinity up here and try to do the arithmetic with infinity. The key is to have a finite thing and then take a limit of it later. Okay? So what I got here is half of what I want to talk about, which is the limit. That's why you get 2. Anyway, this is an example of something called a geometric series. And you have to be careful, and you guys will make mistakes just like I just did in a second if you're not careful. This is a terminology for what's called a geometric series. Now, if I write this out, and this is dangerous, if I write this out, I don't like r to the 0 power. This means, what this actually means is a plus the sum from 2 to infinity, ar to the k minus 1, where all the rest of these things mean powers. 2, when I put 2 in here, I get 2 minus 1. That's r to the first power. When I put 3, I get squared. When I put 4, and so forth. But the notation is supposed to help you. The problem here is that this means power. But if k is 1, r to the 0 power, now we have to try to decide what is something to the 0 power. The notation, what we're trying to do when I did this problem, you have this a1, a2, a3. I had 1 plus a half plus a third and so on. I want this 1 to be 1. I don't want it to be something to the 0 power. Okay. So technically speaking, when I have something like this with a possible 0 power, the meaning of it is this is not something to 0 power. The first thing here is a. This is 1. If you want to interpret this as true, you can say that. The trouble with that is if r is 0, we have 0 to the 0 power, and that's not always 1. As long as r is not 0, you can interpret this as r to the 0 power, you can interpret it as 1. But the symbolism we're choosing has an ambiguity there. And we don't really like symbolism, which is supposed to make it easier, to make it more complicated. But this symbolism is more complicated by its nature. So instead of that, some people say, well, just start doing 0 here and make this ar to the k. But that changes 1 minus 1 to 0 directly. This means a plus the sum from 1 to infinity, ar to the k, splitting off the 1 that would have 0 power here. So this is one meaning. This is the same meaning. It's just in one case, we're summing from 1 to infinity, splitting off something and doing this with 2. In the other case, we're starting with 0 and splitting it off and doing it with 1. Now, this can be tricky, but when you have something like this, if you have a series and you say, I think it's geometric, like was this series a while ago, was this, and we had here, if I write k here, I'd have to write 0 here. Or if I had 1 here, I'd have to write 2 to the k minus 1. That's what we had a minute ago, remember? Either one of these is the same thing. Can I make this geometric? Is this a geometric series? Well, if you look at this one and you look at this one right here, I could say a is 1 and r is a half. That makes it a geometric series. Okay. Now, so what we do, instead of doing something with a half here, what we do is do the same game I just played with the series a plus k equals 1 to infinity, a r to the k, and we call that s, and I'm going to change this to n. Sn is this. We multiply by r, okay, and we will get ar plus the sum from 1 to n of ar to the k plus 1, and then we sort of say, hey, now I have ar, so I can make this the sum from 0 to n of ar to the k plus 1, but I don't like that, so then I'm going to change that by changing the meaning of the subscript. So if I down this by 1, so I get ar here to the k, that's the same thing. And anyway, what I'm going to do now is subtract the second thing from the first, like I did twice already. In this case, what I forgot to do last time was 1 minus r here, s sub n. And I do that, what will happen when I subtract this one from this one? All of these things and all of these things, how do they differ? They differ by, they have this one has this one doesn't have that. The second term here is the first term here. But when I let n be, k be n here, I get n plus 1, and this one doesn't have that. So when I subtract these two, I'm going to get a minus ar to the n plus 1, I believe. Anyway, I'm just doing this fast, but you get something like this. And then we rewrite, and what we have is Sn will be a times 1 minus r to the n plus 1 over 1 minus r. And so you do the arithmetic. This is in the book. I'm trying to do it fast because of the time, but you'll get something like this. And what you do is you let n go to infinity. Here's the n here. This is r. When does this have a limit? Well, it has a limit when r is less than 1. When r is less than 1, this converges to a over 1 minus r. So you can go through this more carefully than I just did. I did it quickly, but it's in the book. Okay. The idea is if I have a geometric series like this, it will converge to a over 1 minus r if the r is less than 1 in absolute value. And I didn't take into case here about absolute value, but, and I'm not quite sure about this right this second because I did it pretty fast. Anyway, but if the r is less than 1, then the sum thing will sum up to this. So one of the things you'll be doing in this section is taking a geometric series, writing it down properly, and then taking a limit of the sequence of partial sums to see what the series sums up to. So I'm going to do some examples of that. And our problem is always time. So in section 11.2, we have the geometric series is defined on 749. And basically, by the way, in the book, it has r to the n, not r to the n plus 1. And so I'd have to be careful about this stuff I did right here, but it's the same idea. And what I want to do is to find an example. And in the exercises at the end of the section, there's several examples. And so just a second. What about summing from 1 to infinity? So I'm going to do a problem here. What about summing from 1 to infinity? So if I say k, I can set let any letter be here. This thing, and it's going to be, in my case, minus 3 to the k minus 1, minus 3 to the k minus 1 over 4 to the k. Now, this is actually problem 23 in the book, but the book uses n here, I'm using k. If I use n here, I'd have an n minus 1 and an n here. Doesn't matter, but I like to use k so that when I do a partial sum, I can do n here. If you do n here, then you have to name the partial thing something different. That's why I prefer to use k, but you can use n if you want. No matter what I do, people do what they want to do, and whether it's right or not. Anyway, so how do I sum this up? Notice I've written it down. I don't know if it has an answer, but if there is an answer, I will equate it to that thing. And I'll say the sum equals something. Well, this is going to be geometric because it looks geometric. It's powers, except it doesn't really. So I'm going to split out 1/4, so I can write this as minus 3/4 k minus 1. Now, the game is to do one of two things. Either to have this like this, or to have this like this. These are the two forms. Either one of them works. And in this particular problem, I have a 1 at the bottom and I have a k minus 1. I have that because I split off the 4k here to 4 times 4 to the k minus 1, and I combine. Once I have this, I can see A and I can see R. It's geometric. So what's the sum of the series? A over 1 minus R. It's 1/4 over 1 minus 3/4. So it's 1/4, and you can put the 1/4 outside if you want. 1 minus 3/4 is 1 plus 3/4, which is 7/4. And so you can write that as 4/7 if you want, or you could have canceled, but the 4's will cancel. Don't multiply things out, and you will get 1/7 as the sum. If I didn't make a dumb mistake. Now, dumb mistakes can be made here because it's A over 1 minus R, but the minus was in the 3/4 here. That's another minus. That can be a mistake. Otherwise, some of you have trouble making simple fractions out of more complicated fractions. But the key is to make the thing you get into one of these two things. Okay, let's do another problem. If I can find another one that's relevant. Looking for, okay, 1, 2, 4. Okay. How about 20 after, so I guess I can't. Anyway, one of the things in section 2 in 11 is dealing with geometric series. Okay, that's one of the things that you will have exercises to do. This section has other things in it as well, and those other things we'll talk about on Monday, but the first part of this section is about geometric series. So I'm going to cut off the recording here.